Hi, so this is the our practice for chapter 8, and I think the chapter 8 is the most important and most difficult chapter in our class in this semester. So I think you should be careful of the contents and any grammar in the R programming related to using the this chapter 8 material. So I think it is nothing but just combining all of the knowledge from the other previous lectures for this chapter 8. So if you're not familiar with the knowledge about the previous lecture, you will have some difficulty in understanding or implementing the R code and learning how to use this one. And however, otherwise, if you have a, if you are fully, if you fully understand the previous lecture, I think there will be no difficulty in understanding today's lecture. But so, uh, please watch out for the upcoming content. And actually, there are five situation or six situation that we are going to deal with for our when we construct our population uh, confidence interval or making some hypothesis test. So I think the most important thing is that the situation where we have to compare two population means. So uh, actually, we have when we construct the confidence interval or when we construct the hypothesis testing, there was always one population. So we always tested if our population or population mean is equal to some value or not. However, from now on, we are going to deal with two population and compare to each other. So there are always two population, and we are going to have a construct some confidence interval or make some hypothesis testing about two population. So as you already know, when although we start with this situation, we can convert the previous situation into this one. And if we change this formula into the right side formula, we can uh, we can deal with this as a one population thing. So we can also apply the previous lecture knowledge into this situation. So we can also do the uh, same test on this situation. So it is the same as the previous one, but the only the difference is that we are going to deal with the two population uh, by deducting one population mean from the other population mean. So there is a expected value and variance of the difference between two sample mean. So if we deduct the sample mean from the other sample mean, it also has the normal distribution with this mean and this variance. So when they are satisfied with they they satisfy this consumption, this normal assumption. Sorry. So we can still use this normal distribution and which means that we can also make our confidence interval or hypothesis testing based on the population mean. So there are still three cases, even though we are dealing with the two population means. So as you already know, if we know the noun, yeah, let me do it step by step. So the first thing is that we know all the sigma squared, which is the population variance of the two population. Then it is easy. So because we know that the difference between two sample mean follow the normal distribution with this mean mu minus mu two and variance as this value. So which means that if we standardize this value, it follows the this test statistic follow the normal distribution, standard normal distribution, which also means that we can construct the 100 multiplied by 1 minus alpha percent confidence interval by using this formula. So we can start the first example. It says that it follows the normal distribution and it also gives us the population variance. So which means that we know all of the population variance of all of the populations. So which is 25 and 16 from each other. And we want to make some 95% confidence interval for the sample mean. I mean the sample mean difference from each other. This is the sample 1, sample 2. So this is the first file of the chapter 8 revision version. So I stored each vector, each sample into my own variable a and b. So after you run this code, you can see that you have two variable full of your own values, as this problem suggests us. And we know that this statistic follows the normal distribution. So what you have to do is just getting the same value by using the sample mean and the population mean from our assumption and the variance value, which is the same as this one. So this variance value comes from this formula. So I use the same formula by using the square root function and the sample number of the sample from each population and the variance from each population. So you can see that our test statistic Z0 has this value 6.94, which is the same as this value here. So it is nothing but we calculated the test statistic based on this problem. And it is very easy because we didn't calculate all the thing by our own hand. We just used the R programming, and R programming gave us the calculated value. So it is very convenient, as you can see, and we want to get p-value here and the 95% confidence interval. So as I already know, because we are dealing with a two-sided test, we have to multiply the p-norm, the result of the p-norm by 2, which is the p-value in this situation. So it is very much less than the significance level, which is 0.05. We are able to reject the null hypothesis and go to the alternative hypothesis, and that's it. And as you also apply this information into the confidence interval, you can see that you have these two values, lower bound and upper bound for our confidence interval, which is the same as this screen value. And before going to the next problem, this is the code for helping us to see the value from the scientific number, because before we run this code, you can see only you cannot see this value. There will be some weird value which is expressed as expressed with a sign E, I mean alphabet E, but because it is the scientific number, we have to transform the scientific number into the numerical number so that we can see and check if the result is less than or equal to the significance level. For that, we have to run this code. So it is not as important, but I think it will be helpful for you to see the result more conveniently and more intuitively to you. And the next example is this one. And oh yeah, I'm sorry, and there's more. There's one more update. So I think I remember that uh, I used the variance of the each sample when we solved this example number one. However, because we have to use the sigma squared here, and sigma squared comes from this problem, not our sample. So we have to use the value directly from the problem. So we must not use the standard deviation of each sample. So make sure that I I modify the number here. So please do not be confused. Oh, so I marked as revision when I updated the from the previous version. So please check it. And next example is example 9.1 here. And actually the solving process is the same as the previous one. We know that our sample comes from the normal distribution. Maybe here? Yeah, our normal. So we know that our sample comes from the normal distribution, and we know all the variance of the population of the each population. So the solving problem has to be same as the previous one, example number one. So I prepared uh, the code for solving this problem. So this example. So I think you can run this code and check if your answer is same as the sum. And I also marked the revision here because I updated the code from the previous one, so do not be confused. I think this is more closer to the answer. And the next situation is that uh, it is still compare. It is still the situation where we have to compare two population means, but in this situation we don't know the population variances from each population. So actually there are also two cases even in this one situation. So you also have to classify the each situation and follow the each process based on the information. So actually there are always sigma squared 1 and sigma squared 2 from each population. So population 1 has the variance 1, population variance 1, and population 2 also has the uh, population variance 2, which is sigma squared 2. But it depends on the two values. So if the two groups have same population variance, so in this situation we call it homogeneity of variance. Otherwise, the population variance is different from each other. For example, in this situation, we call it heterogeneity of variance. So we have to divide the situation into two cases. So the first case is the homogeneity of variance. So when we uh, confront the homogeneity of variance, we have to get the variance of the sample mean, difference of the sample mean with this formula. This and this is called, as you already know, crude sample variance, and crude sample variance formula is here, which is very complicated. So for example, if we have this information, the crude sample variance is this one by using this formula. So as you already know, this is our sample mean, difference of the sample means, and this is the population difference of the population means, but it has to be 0 of the right side because we assume that our population mean has the same value. Yeah, here in the null hypothesis. And this is the normalizing constant so that we have to calculate this value when we deal with the homogeneity of variance. So, and it is well known that this test statistic follows the t distribution with this degree of freedom. It is we do not prove the result of this one, but we have to accept the result. So what you have to do is just remembering the formula and remembering the situation that this test statistic follow this t distribution with degree of freedom of the value, which is the sample size 1 plus sample size 2 minus 2. And the confidence interval is this one. So we can deal with the second example here, but actually it use the same sample, so the mean and variance is the same as each other, and by using this formula we can get the per sample variance, which is 29.6155 here, which you can see here. The per sample variance is the same as this one, 29 here. And then, which means that we can also make our test statistic by using this formula and this code. So the formula is the same as this one, like this one, and this value goes to the here, this part, and yeah, so it says that about 5.78, which is the same as 5.78. So we can see that if we correctly make our R code, we don't have to calculate all the things by our own hand, because our programming helps us calculate all the things very conveniently and very very accurately and very fast. So if you are familiar with using R programming, yeah, there will be a lot of benefit from using this programming rather than just a calculator. And then we have to get the p-value and the 95% confidence interval here, which is the same as this code. So if you see the result of the PT function multiplied by 2, as we are dealing with a two-sided test, is much less than 0.05, which is the significance level here. So we are able to reject the null hypothesis for now. And then the confidence interval is this one, which is the same as 2 bound, which is lower bound, and upper bound, same as this material. So you can also refer to this explanation here. And I left this example 9.1 as an exercise for you. So there is no code I prepared for you, but because the solving process is the same as the previous one, example number 2, there will be no difficulty in implementing or getting the answer of this example, as you are already are able to understand all the previous things. And additionally, actually, there is this process is some process we used to get the answer for constructing the confidence interval or getting the p-value of our hypothesis test. But actually, there is also our programming function, innate function, that implement the hypothesis test instead of us. So if you make the data frame with this one, and if you put the data frame into the argument of the t.test function with the adequate argument, you can get also the same result. So because we are dealing with a homogeneity situation, the variance that equal option is true, and yeah. So if you have any question about the t.test function, you can run this code with the question mark, and you can see the usage of this t.test function. So, or there is also Google or ChatGPT you can ask to. So yeah, actually I do not usually recommend using this kind of function because there is a lot of situation where we can be confused of when using this kind of function, because if we construct all the process and if we calculate all the test statistic and put sample variance and our own PT function, it is very intuitive and we can understand all the thing in this process by following the process fully. However, so that we can be sure about our result of our but if we use just a function with some argument which is very confusing, I think there will be a lot of situation that we can be trapped, so that we can make some mistake by when using this kind of function. So I usually do not recommend using this kind of function because you can take some mistake. There will be some mistake when using this kind of function, but I just wanted to say that there is also a function that our programming gives us when doing the same thing. So yeah, just pick as your own your decision. And the next is the heterogeneity of variance. So the variance is different from each other. In this situation, we get the variance of the difference of the two sample by using this formula, and the test statistic is the same as this one, and it follows the t distribution with the degree of freedom as this one. It is very, very, very so complicated formula, but it is the fact. So you have to accept this result and memorize, or how you have to now how to use this formula in your examination or in your homework. So, and then the confidence interval formula is the same as this one. And for this example, we use the same sample. And actually, we are doing the same thing, but in different situations. So we have to follow this process when getting the test statistic or getting the confidence interval. And it says that our degree of freedom in the t distribution is about this one, which is this one, because we have to deal with the natural number. And it says that T0 test statistic is about 5.78, and p-value is much less than 0.05, and confidence interval is like this one. And I got all the thing the same as the previous one. So you can see that the degree freedom is same as the 17.495, which is the same as this one. And the test statistic is about 5.77 here. And the p-value and confidence interval is here. So p-value here, and the confidence lower bound and upper bound and upper bound here. So you can refer to the material and also the as well as the code I prepared for you. And there is also the t-test function because we are using this is the same similar situation, but you have to set the variance that equal option as first because this situation is about heterogeneity variance here in this example number 3. And then this is the time to go to the next station, which is the right sample approximation. And I also left the example, this one, as an exercise, so doing yourself. And we already know that if we are not sure that our sample comes from the normal distribution, if the sample size is large enough so that we can use the CLT, central limit theorem, we are sure that we can say that we use the large sample approximation so that this test statistic also follows the normal distribution based on the central limit theorem. So this is the information, and we know that if after we get this statistic, we can construct the confidence interval here. So this is, yeah. So by using this formula and this information, you can see that the test statistic is about 20.75. So let me implement the same code. So you can see that this code gives us the value as the 20.75 as the test statistic, which is the same as this one here. And because we are dealing with the two-sided test, you have to multiply the result of the p-norm function by 2. And you can see that the result is a lot less than the significance level. So we can reject the null hypothesis, and the confidence interval by using this formula is the same as this one. So the lower bound is about 9.59 and the upper bound is about 11.60. Oh yeah, so I think my code is correct, and the material is there's a typo because we use when we construct our confidence interval, we use this formula, and N1 is 100 here, and N2 is 90 here, and S1, I mean S1 squared is here, and S2 squared is here, 1311. But so it is the same as this one. So until this thing, we are doing well. However, in this situation, it is different. So it has to be 100, and it has to be 90, and it has to be 13, some blah blah, and this has to be 11 point blah blah. So I think this formula is a typo, and my code is more correct version. So you have to be sure that the answer is the lower bound and upper bound is this one here. So make sure that this is a typo here. And I also left the example 9.1 as your exercise. So yeah, doing yourself, please. And this is the first chapter of the chapter 8. So let's go to the chapter 2 of the chapter 8. I mean, yeah, the second version, the second part of the chapter 8. So it's very short. So let me do it shortly. So the next situation is that we construct when our experiment is about the paired difference test. So the pair data is somewhat different from the previous one because we are dealing with the same individual, or we are dealing with the same experiment object, so that we observe the each data with along with different points in time. So there has to be before data and after data, and the after by getting the difference from two data, we have to get the difference data, and we make some assumption, and we construct our confidence interval or make some hypothesis test based on this difference data from the before and after data. So you have to be sure that when you see the problem, when you see the example, and if you see that it is telling it some experiment about the before and after data, you have to be sure that you are following this situation. So you have to recognize that this is about the paired difference test and use this formula in that situation. So as we already have done, our test statistic, this formula follows the t distribution with the degree of freedom as n-1, and our confidence interval also has this value. And this is known fact, so you have to accept, even though you can understand the whole of the proof of the derivation of this whole procedure. So let's go to the example number 5. Because we are dealing with the before and after data, this is the paired difference test, and then we have to follow this formula. We have to use this formula. So this is the difference data, and by using this difference data, we get the mean and variance of the difference data, and test the statistic by using this formula follows the t distribution, so that with this value, so that we can get the p value, and we can also construct the confidence interval of the paired difference population mean, because we can use the t distribution from now on. So this is nothing but getting the pair t test. So this is the before data and after data, and sorry, this also has to be the revision, I think, because we have to deduct the after data from the before data, like this one here. So if we deduct the vector from the vector, the result comes from the each calculation. So let's see. So it also has the 10 value as the result of the difference calculation, because it calculates element wise, so that it calculates the difference between two vector, the element by element, so that we can get each calculated result from the difference calculation. So because it is fact, and then we have to get the mean and variance of the difference vector, so that, and then you can see that the test statistic here is the same as 0.42. Mm, yeah, I'm sorry. So I think we have to. I think it doesn't matter. So, but I think it is important that um, we have to be we are consistent about uh, about doing the formula. So I think we don't have to multiply this one, and we have to get the difference like this one. So that we have the same difference data with here. So you can see that the data is the same as the material. So that after getting the mean and variance of the difference data, you can see that the t statistic has this value minus 0.426 like this one. And then by using the PT function and the confidence interval, you can see that the p-value is about 0.34 here. And the confidence interval is about the same as this bounds. So because our p-value is more than the significance level, we cannot reject the null hypothesis in this situation. And I also leave this example as your exercise. And this is the final thing. So, sorry. And yeah, so actually there is also the t-test function here. So in this t-test function, there is also paired option. So after you set the paired option as true, you can also use the t-test function, even though you are dealing with a paired t-test. So yeah, just use if you want to be want to you want to get the result more conveniently. So you can see that it also gives also the same result from previous one. And this is the last thing. So we have done with the three population means. The three situation about population mean, and the fourth situation is about paired difference test. And the fifth situation is that we are dealing with the two population proportions. So there is two population proportions, and then we can get the sample proportion and get the difference from each other. And then if we get this test statistic, we know that it follows the standard normal distribution. So that we know we can use the confidence interval, or we can also do the hypothesis testing. So this is the example, and there are the process here and all the information here, and you can get the test statistic as this one about 2.84. So let's say that our test statistic has the 2.84 here. I think this is the typo here, finally, really, because so our test statistic is this one, and this is the positive value because this is the square root value, and this is the PA bar minus PB bar, and PA bar minus PA bar is 0.35, and PB bar is 0.55. So it has to be minus 0.20. So this test statistic Z0 has to be minus less than 0. So I think this should be the minus 2.84 here. So this is why I got the result as minus 2.84. And it doesn't, I think it didn't affect the result of this p-value or confidence interval, because as we are dealing with a two-sided test, so yeah, because we just multiply the result of the p-norm function by 2. So you can say that the p-norm function, the p-value is much less than the significance level, which is the 0.05. And our confidence interval also has this kind of value here. So that's it. This is the end of the class, and I think the chapter 8, as I already said, is the most important and most complicated and most difficult chapter of all the chapters. So so good luck, and you have to be familiar with using or implementing the R code and formula based on the situation. So you have to classify the situation when you see the example. It is the most important part. So okay, have a good day and see you next time. And I will shortly sum up it this lecture by using Korean. 네, 어쨌든 수고하셨고요. 되게 간단하게 끝낼 건데 뭔가 컨피던스 인터벌을 세우는 거나 가설 검증을 해왔잖아요. 근데 그거는 저희가 파퓰레이션이 한 개일 수도 얘기고 챕터 8부터는 2개를 가지고 하는 거죠. 그래서 이제 그 파퓰레이션의 차이가 어떤지, 처음엔 민을 했었죠. 근데 그 민일 때도 처음에는 베리언스를 다 할 때, 두 번째는 베리언스를 다 하는데 둘이 같을 때, 세 번째는 베리언스를 다 하는데 둘이 다를 때, 다 모르는데, 죄송해요. 첫 번째는 다 할 때, 두 번째는 다 모르는데 둘이 같은 건 할 때, 세 번째는 다 모르는데 둘이 다른 건 또 할 때, 네 번째는 페어드 티 테스트였고요. 시범 데이터죠. 애프터 리뷰랑 비포 데이터가 있을 때. 다섯 번째는 population proportion이죠. 민이 아니라. 여기 네 개까지는 population mean, 다섯 번째는 population proportion. 이 세 개는 특히 population mean인데 베리언스를 아는지 모르는지 같은지 다른지 알 때랑 그런 거 봐서 사실 하는 과정은 다 똑같아요. 그러니까 식만 알고 있으면 문제를 봤을 때 어느 상황인지 알고 그거에 따라서 똑같이 하기만 하면 돼요. 근데 제가 하고 싶었던 말은 뭐 포뮬라도 알고 있으면 되고 상황도 그거에 따라 구분하면 되는 건데 이런 거 되게 복잡하잖아요. 어쨌든 예를 들어서 풀드 뭐 그런 거 이것저것 계산할 때 예를 들어 이런 걸 다 계산해야 되잖아요. 근데 이게 워낙에 실수하기 좋게 생긴 공식들이죠. 어떻게 보면 저희가 되게 복잡하고 문제도 그러니까 웬만하면 사실은 R 프로그래밍을 쓰면 R 프로그래밍은 사실 계산 실수는 안 하거든요. 그렇기 때문에 좀 더 정확하고 어떻게 보면 이해만 잘한다면 좀 더 편리하게 결과를 구할 수 있다는 뜻이 되는 것 같습니다. 그러면 수고하셨고 학기 막바지만큼 더 열심히 잘 해주시면 되겠습니다. 감사합니다.